Welcome to the continuation of the lectures for MA 102 and MA 103. My name is Amol Sasane and I'll give the rest of the lectures in the Michaelmas term for the students of MA 102 and MA 103. And in this part, we will learn about analysis, the foundations of mathematical analysis. And for the students of MA 103, I'll also give the lectures in the first half of the Lent term, weeks 11 to 15. And in this part, we will learn about the number systems and we'll also have a closer look at the set of integers with its arithmetic operations. So what are the organizational changes for the course? Now, first of all, a PDF file of the lecture notes for the part of the course which will be given by me has been posted on the Moodle page. And these lecture notes cover weeks 6 to 15 of MA 103. So these lecture notes have 5 chapters. And chapters 1, 2 and 3 are for students of MA 102 and MA 103. And this covers the remainder of the Michaelmas term, so weeks 6 to 10. And this part is the part on the foundations of mathematical analysis. But the same lecture notes also contain chapters 4 and 5. And this is for students of MA 103 only because it covers weeks 11 to 15 of the Lent term, and this part is on number systems and this part will be given by me. Okay, so somehow it was convenient to have one PDF file because the theorems in these 5 chapters, they refer to each other, and so it was good to have it in one file. But to repeat, for students of MA 102, only chapters 1, 2 and 3 are relevant, and for students of MA 103, all of these 5 chapters are relevant. Okay, and these lecture notes cover the part of the course which will be given by me, which is basically weeks 6 to 15. Now these lecture notes have numbered exercises like 1.7, 2.20 and so on. And as the weekly homework, I'll select a few of these exercises from the lecture notes and assign them as the homework. Okay, but everything else remains the same. So the homework will still be weekly, it will still be assessed, discussed in the exercise classes and so on. All that changes is that the homework problems will be a selection of exercises from the lecture notes, and this will be posted in the homework schedule, which ones you have to do every week. Okay, and there are many more exercises in the lecture notes than the ones which will be assigned to you as homework. And the solutions to all of these exercises will eventually be posted on Moodle on a rolling basis. I'll also run the question and answer session. And so if you have questions or you need clarifications, please let me know the week before so that we can then discuss it in the next question and answer session. And in these sessions, I also plan to do some extra examples and so on. So in the remainder of the Michaelmas term for students of MA 102 and MA 103, we are going to study analysis. So what is analysis? Well, analysis is of course a word in English, but what does it mean in mathematics? In mathematics, analysis refers to the subject of mathematical analysis, which is the subject where calculus is made rigorous. And we have some idea of what calculus is. But this mathematical analysis is itself a big branch of mathematics where there are several subdisciplines. There is real analysis, there is complex analysis, functional analysis and so on. But what we are going to study is real analysis, which is analysis where the underlying number system is the set of real numbers, R. Okay, so the word analysis in mathematics refers to calculus made rigorous, and we are going to study real analysis where the calculus is done using the real number system, R. And we have some notion of what calculus is. In calculus, there are two main themes. One is differentiation and the other is integration. In differentiation, one talks about the rate of change of a function at a point. So that's a local picture. And in integration, we talk about adding up values over an interval. And so that's a global picture. And the main result in calculus is that these two worlds of differentiation and integration are related to each other. So that's the fundamental theorem of calculus. And this fundamental theorem offers some computational ease or calculational ease in problems. And for that reason, this subject is called calculus. But calculus is not what we are going to study in this course, but we are going to focus on this made rigorous part. So we are going to learn about the foundations of calculus. So it turns out that behind these various concepts of differentiation, integration and so on in calculus, there are often limiting processes involved. And so in order to define these notions rigorously and to prove theorems about them, we first need to study the set of real numbers R. And it turns out that all the nice theorems and nice machinery in calculus is possible because this set of real numbers possess a certain property known as the least upper bound property of R. And this property is not possessed by some simpler number systems. For example, the set of rational numbers does not have this least upper bound property. And so calculus simply does not work with this simpler number system of rationals. And that's why we need the set of real numbers which has this property, and then it's possible to prove these nice theorems in calculus. So we'll start the course by studying the real numbers and this least upper bound property of R. And then the plan is to also look at the first steps in analysis. So we will learn the concept of the limit of a convergent sequence, and then we'll also discuss continuity of functions and the nice properties possessed by continuous functions. So these are the first steps or the foundations of analysis. And of course, in later courses, for example, MA 203, you will proceed from these foundations and go further. Then you will study differentiation, integration, and so on. So we will cover three topics in analysis: the real number system and the least upper bound property of R, sequences and their convergence, and continuity of functions. And I mentioned that the set of real numbers has this least upper bound property, but that is not possessed by some simpler number systems, like the set of rational numbers does not possess the least upper bound property. So let me give you a glimpse of how things might go wrong if one tries to do calculus with Q. So let's take a typical problem in calculus, for example, that of determining the area under the graph of a function, and suppose that the function is given by f of x is equal to 1 by x for positive x's. And suppose we want to determine the area under the graph of this function in between 1 and 2. So this is what the graph looks like. And then you may have learned that the area is given by an integral from 1 to 2 of 1 by x dx. And that turns out to be log 2. And it can be shown that this is not a rational number. So we are forced to leave the set of rational numbers. But let us consider how we think of this area. Well, in calculus we use the method of exhaustion. So we draw rectangles, and by making them finer and finer, if we calculate the sum of these rectangular areas, then this sum approaches this final area that we have in mind as the rectangles become finer and finer. Now suppose that we insist that at each stage of this process we end up with a rational quantity, and then see if we can get away by calculating this area by using only rational numbers. Okay. Now in order to ensure that at each stage you have a rational area, I proceed as follows. First I bisect this segment. So this is 3 by 2, and then at the first stage I have these two rectangles. If I add up their areas, that gives me a rational number, and I denote that by A1. Then at the next step, in order to still get a rational number, I simply bisect these two segments, and then I get these four rectangles. If I take the sum of their areas and I call that A2, we can see that this A2 is also a rational number. And then I continue this process. I bisect each of these, I get 8 rectangles, and I again get a rational number A3. And in general, at the nth stage, it turns out that the sum of the rectangular areas that I get is given by this expression. Okay, so you can accept this on faith. Don't worry about deriving that right now. But the message is that this an is a rational number. So at each stage, I have a rational number, and we see that visibly these areas are increasing. So A1 is less than or equal to A2 is less than or equal to A3, and moreover each of these areas is less than this final area, and let's denote that area by A. So this capital A is a number which is bigger than each of these areas. You see that in each of these cases there is this white portion, so the area is somewhat smaller than this total area. Okay, so this capital A should be a number which is bigger than each of these, and since at the nth stage where n is very very large, say a million or something, there is very little area left out over here. So this capital A is certainly a number which is bigger than all of these, but it's the smallest such one. Okay, so this area is an upper bound for these numbers in the sense that it's a number which is bigger than each of these, but it's the smallest such upper bound, okay, because these numbers are approaching this final area A. So we ask the question, well, does there exist a rational number capital A which is bigger than each of these and it's the smallest such? And remarkably, the answer is in fact no. So there is no rational number which is bigger than each of these and is the least such upper bound. Okay, and this problem arises because this Q does not have this least upper bound property. And so one simply cannot do calculus with the set of rational numbers, but with the set of real numbers, it does have this least upper bound property, which as yet we have not yet defined. We'll soon do that. But that's what makes calculus work. Okay, so don't worry too much about this example. This was just some motivation, or rather a discussion, to point out that with the set of rational numbers there is a problem which is then remedied by the set of real numbers. Okay, so the set of rational numbers does not have this least upper bound property. As yet we have not yet defined what that is, but we'll do that today, and we will actually see an example where we rigorously show that this does not have this least upper bound property. But on the other hand, the set of real numbers has this least upper bound property, and that's what makes calculus work. And since analysis is calculus made rigorous, that's where our journey will begin. We'll first understand what is this least upper bound property of R. So here is the plan for the Michaelmas term, which is the next 5 weeks, and this is for students of MA 102 and MA 103. The plan is to cover the first 3 chapters of my lecture notes. So in chapter 1, we will study the real numbers and this least upper bound property of R. And then we will learn about 2 foundational concepts in analysis. One is on sequences, and when we say that a real sequence converges with a limit. Okay, so this very important notion of a limit of a sequence. And then in chapter 3, we will look at continuous functions and their nice properties. Among them are what is known as the intermediate value theorem and the extreme value theorem. Okay, but in this first chapter, we hit the ground running in the sense that we do not really look at what the construction of R is. So what is really R as a mathematical object? And that will be covered in the Lent term, and that is for students of MA 103 only. So in the Lent term, the plan is as follows. For the part which is given by me, which is weeks 11 to 15, we will cover chapters 4 and 5 of my lecture notes. In chapter 4, we will look at number systems. So starting with the set of natural numbers, we'll construct the integers, the rational numbers, and finally the real numbers. So over here, we will learn the construction of the real numbers. What is the set of real numbers as a mathematical object? So that will be learned over here. And many of the properties which we have taken for granted so far in this course for the operations of arithmetic in each of these number systems, we will actually prove over here that all those properties work. And in chapter 5, we will have a closer look at the set of integers and its arithmetic operations and talk about things like divisibility, the greatest common divisor, prime numbers, and the fundamental theorem of arithmetic. Okay, so that's the plan for the part of the course that I will be giving. We will now begin with chapter 1, which is on the real numbers, and the goal in this chapter is to understand what this least upper bound property of R is. So we should have some understanding of what the set of real numbers is, and we may think of the real numbers as numbers having a decimal expansion, or we might think of them as points on the number line. So recall that the number line is a line where we have chosen an origin and a unit length so that we know where this 1 is, and then we can reproduce this length over and over again so that we have 2, 3, 4 on the one hand and -1, -2, -3 on the other hand. And we also have, besides these integers, also the rational numbers, for example 5 by 2, minus 1.3 and so on, and also some irrational numbers like square root of 2. And all the points on the number line is what we think of as the set of real numbers. But this is just an intuitive picture of R, and it's not a precise mathematical definition. So one might ask, what is this set R as a mathematical object? For students of MA 103 in the length term, we will actually learn about the construction of R, and there we will learn what is this set precisely. But for MA 102 students, for now, we will accept R to be an undefined set, but nevertheless we will state its properties precisely, and these are the properties which we are allowed to use. Okay. And some of these properties are familiar to us. For example, we know that real numbers can be added and they can be multiplied, and these two operations have certain properties. Okay, the usual arithmetic rules. So these are listed in the lecture notes, and these are things that we are allowed to use. So these are the familiar rules of addition and multiplication. And there is also this order relation which allows us to compare real numbers. 1 is less than 2 and the square of any real number is bigger than or equal to 0 and so on. And this can also be stated precisely. So we have this. And finally, with these two as the starting point and accepting that this R is a set having these properties, we will learn what is this least upper bound property of the real numbers. Now, it might still make a few of you uncomfortable as to what this set R is exactly as a mathematical object. Now, it turns out that this construction of R is a complicated thing to do, which takes time to do properly, and that is why it's not included in MA 102, but as I mentioned in MA 103, in the length term, we will do this. So for now, we will simply accept that R is an undefined set which has these precisely stated properties which we are allowed to use, and that will be our starting point. So the goal now is that, well, these two properties we are familiar with, but the goal in this first chapter is to understand what is this least upper bound property of R. So let me recall the notion of the number line, our intuitive understanding of the real numbers. So what is the number line? Well, first of all, it's a line on which we have chosen an origin. We have simply marked off a point which we think of as corresponding to the number 0, and then we take any unit length, something that we decide, and mark off a point on the right at that unit length, and that we think of as 1. And then by repeating this unit length over and over again towards the right, we get all the integers 2, 3, 4 and so on, and we can mark off this length repeatedly on the left hand side, and in that way we get these milestone points which are the negative integers, -1, -2, -3 and so on. And this unit length we can divide into any number of parts. For example, I can divide it into 8 parts, 8 equal parts, and in that way I get the length 1 by 8. Okay, so I get the fraction 1 by 8 over here. And then by repeating this an integer number of times, I can get any fraction with the denominator 8. For example, if I repeat this 9 times towards the right, then this point will correspond to 9 by 8. And then the negative fractions will be obtained by just repeating this length on the other side at that same distance from the origin. Okay, so this length was 9 by 8. If I reproduce that on the left hand side, then this point corresponds to -9 by 8. So in this way I also get all the fractions. Okay, instead of dividing into 8 equal parts, whatever denominator I have, I can divide it into this unit length into that many number of equal parts, and then the fraction can be obtained by taking whatever the numerator is. If it is positive, you simply repeat it towards the right as many times, and the negative ones are obtained by reflection on the left. Okay. Now, in this way, we have got all the rational numbers on the number line, and a natural question is, does this exhaust the number line? Is there something more on the number line? Okay, and the answer is, well, this does not exist the number line. So there are points over here which correspond to non-rational numbers. And to see this, here is sort of a geometric proof of that. So this was the unit length. If I erect it again at a 90-degree angle, then I get this right angle triangle. Now this is length 1 and this is length 1. And by Pythagoras theorem, I know that the square of the length of the hypotenuse is equal to the sum of the squares of the other two sides. So then we know that the length of the hypotenuse will be the square root of the sum of the squares of the other two sides. So this length will be square root of 1 square plus 1 square, right? In other words, it will be square root of 2. So this length is square root of 2. Now taking this as center and this as radius, I can draw a circular arc which will intersect somewhere on the real line. And let's notice that this distance, since it's the radius, is also this distance because that's the radius, and so this distance will be root 2. But we have seen earlier that root 2 is not a rational number. So here is a point on the number line, namely this root 2, this point over here, which is not a rational number. So the number line contains, besides the rational number points, also these other numbers, the irrational numbers, okay? And all the points on the number line that we have, that we intuitively think of as the set of real numbers, okay? So this gives us some mental picture of what the real numbers are, okay? But this is still an intuitive picture, and we can also think of the real numbers as numbers having a decimal expansion. So that is our intuitive understanding of the real numbers as points on the number line or numbers having decimal expansions. But that's of course not a precise mathematical definition. And as I mentioned earlier, for students of MA 103, in the length term, we will learn about the construction of R as a mathematical object. But for now, we simply accept R as an undefined set having certain precise properties. Of course, some of these properties are familiar to us, so we take for granted the usual arithmetic rules of real number addition and multiplication. So we accept that R is a set with two operations, addition, which takes two real numbers and produces their sum, and the operation of multiplication, which takes two real numbers and produces their product. For example, 3 times minus 3 is equal to minus 9, and 3 by 2 times 4 is equal to 6, and so on. And these two operations have certain arithmetic rules. So these are listed in section 1.2, and here I list one of them. For example, the fact that this operation of multiplication distributes over addition. So if you have three real numbers a, b and c, then a times the sum of b plus c is the same as a times b plus a times c. And then we also have the order relation, and this allows one to compare real numbers. For example, 0 is strictly less than 1 and so on. And this order relation has a certain arithmetic consistency with these two operations. So for example, we are familiar with rules like the following. If you have two real numbers a and b such that a is strictly less than b, and you have another real number x which is positive, so x is strictly bigger than 0, then you have that a times x is strictly less than b times x. So the inequality is preserved when you multiply both sides by this positive real number x. Also, we will use the following very important property of this order relation, which we are familiar with, and I call this the trichotomy law, which says that if a and b are any two real numbers, then one and exactly one of the following three statements holds. Either a is strictly less than b, or a is equal to b, or b is strictly less than a. So one of these three statements has to hold, and exactly one of them holds, so it can't be the case that two of them hold simultaneously. So if we know that a is strictly less than b, then these two cannot happen. If we know that a is equal to b, then these two cannot happen. And if b is strictly less than a, then these two cannot happen. And it's called the trichotomy law because we have this choice between three statements and one of them has to hold. Now, in MA 103, in the length term, after learning about the construction of R as a mathematical object, we will in fact prove the properties that we have listed over here. But for now, we simply take for granted that you have a set of real numbers which has exactly these properties, and this will be our starting point. And chapter 1 really then begins with section 1.4 in the lecture notes. That is, we take these properties for granted and we will learn something new about the real numbers, namely the least upper bound property of R. So that's the goal in this first chapter, to understand what is this least upper bound property of R. So the goal in chapter 1 is to understand this least upper bound property of R, but let's go step by step. So there's a whole bunch of words over here. Least upper bound property of R. So let's forget about this part for now, property of R, and let's also forget about this least word. And so all we are left with is upper bound. And let's first understand what's meant by the upper bound. Upper bound of what? Of any subset S of R. So here is the definition of what's meant by the upper bound of a subset of R. Okay, so let S be a subset of R, any subset of R. Then a real number U, which may or may not belong to S, right now it's just a real number. Then a real number U in R is said to be an upper bound of S if for every element X in S, you have that X is less than or equal to U. So in other words, this number U, this real number U, is bigger than or equal to all the elements of S. Okay, so sort of pictorially, this means the following. You have the set S, okay, so that's a collection of points on the number line, and it's some blob, so maybe it has some segments, it has some points, and so on. So maybe our set S comprises of these orange points. Then an upper bound is any real number which is bigger than all the members of S. Okay, so any point on the right of this set will serve as an upper bound, and then we see that there are lots of these. For example, this is an upper bound because that's bigger than or equal to all the members over here. U prime, which is this point, is also an upper bound of this set because it's bigger than all the members of this set. And in fact, any point on the number line which is to the right of this set, so anywhere on this part of the real line, that will serve as an upper bound for this set. So that's the mental picture that we have. And now let's see some concrete examples. Okay, so suppose our set S is the set comprising the three numbers 1, 2 and 9. So that's a subset of the real numbers. What are some upper bounds for this? For example, 9 is an upper bound for this set because it's bigger than or equal to each of the members of this set. Also 10 is an upper bound for this set because that's bigger than or equal to each of the members of this set. And in fact, any number which is bigger than or equal to 9 will be bigger than or equal to each of the members of this set, and so any number which is bigger than or equal to 9 will serve as an upper bound for this set. Okay, let's consider one more example. Let S be the set of all those real numbers X such that X is strictly less than 1. Okay, so then this has 1 as an upper bound because indeed each member of the set is strictly less than 1, so it's less than or equal to 1, so 1 is certainly an upper bound of the set. In fact, any real number U which is bigger than or equal to 1 is an upper bound of the set because any X belonging to the set is actually strictly less than 1, so this U will certainly be bigger than or equal to any member of the set, and so all of these numbers which are bigger than or equal to 1 serve as an upper bound for this set S. Okay. Does every subset of the real numbers have an upper bound? And the answer is no. So here is an example. Suppose I take the set S to be the set of all the real numbers, and let's convince ourselves that this set has no upper bound. The set of all real numbers, that set has no upper bound. Okay. Now this is intuitively clear because an upper bound was something on the number line which is on the right of the set. But if I take the set to be the whole number line, then there is no room left. There is nothing on the right. Okay, because you have exhausted it all. Okay, but that's not a rigorous proof. So let's give a rigorous proof, and we'll prove this by contradiction. Okay, so let us suppose that this set S of all real numbers, suppose that set has an upper bound. Well, that upper bound will have to be some real number. So let's suppose that U is a real number which serves as an upper bound for this set. Now since U is a real number, U plus 1 is also a real number, and so it belongs to this set S. But since U is an upper bound for the set, this upper bound should be bigger than all the members of the set, in particular this one, U plus 1, which belongs to the set because it's a real number. So you have got that U is bigger than or equal to U plus 1. Now if I add minus U to both sides, I get that 1 is less than or equal to 0, which is clearly false. 1 is strictly bigger than 0. And so this contradiction shows that our original assumption that this set has an upper bound must be false. And so the set of real numbers has no upper bound. So let's consider one more example. Let us take S to be the empty set. Now this empty set is of course a subset of R, and our claim is that every real number u is an upper bound of S. So let's prove this claim. So let u be any real number, and we want to show that this u is an upper bound of S. So we'll prove this by contradiction. Let us suppose that u is not an upper bound of S. Now what does u have to do to be an upper bound? Well, it should be bigger than each of the elements of the set. But since we are assuming that this u is not an upper bound, that means that there must be some bad element in S which prevents this from happening. So there exists some x belonging to the empty set such that x is not less than or equal to u. But there is a problem already over here, because we are saying that there exists an element in the empty set, but we know that there is no element in the empty set. So we have arrived at a contradiction, and this contradiction shows that our original assumption that this u is not an upper bound of S cannot be true. Okay, and so this u is an upper bound of S, and since the choice of u was arbitrary, it follows that every real number is an upper bound of S. So the argument that we have given is a bit like the following. Consider the statement that every person with 6 legs is intelligent. Now that's a true statement because the argument is as follows. Can you show me a person with 6 legs who is not intelligent? And the answer is no, because there is no person with 6 legs. Similarly, the statement that every person with 6 legs is not intelligent is also true, because can you show me a person with 6 legs who is not intelligent? And the answer is no, because there is no person with 6 legs. In fact, every person with 6 legs is blah blah blah, where this blah 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 is anything, any property you like, is a true statement. And again, the argument is that can you show me a person with 6 legs who does not have this property? And the answer is no, because there is no person with 6 legs. So every person with 6 legs is a good cook is a true statement. Every person with 6 legs is not a good cook is also a true statement, and so on. So that's the kind of argument that we gave over here. So we have seen several examples of upper bounds of subsets of the real numbers, and now we give the following definition. If S is a subset of R, then we say that it is bounded above if S has an upper bound. So the set of upper bounds for a set, if it is not empty, then we say that the set is bounded above. For example, the empty set is bounded above because it has a lot of upper bounds. Every real number is an upper bound. Similarly, in our earlier examples, this set is also bounded above because the set of its upper bounds is non-empty. 10 is an upper bound, 9 is an upper bound, and any number bigger than or equal to 9 is an upper bound. So it has lots of upper bounds, and so this set is bounded above. Similarly, this set is also bounded above because it possesses an upper bound, but the set of real numbers is not bounded above because it has no upper bound. So we have now seen the definition of what's meant by the upper bound of a subset of real numbers, and also what's meant by a subset of real numbers as being bounded above. And now let's give the corresponding definitions of lower bound of a set and what's meant by a set being bounded below. So let S be a subset of the set of real numbers, then a real number L is said to be a lower bound of S if it's less than or equal to each of the members of the set. So for every x belonging to S, L is less than or equal to x. And the set is said to be bounded below if S has a lower bound. So the set of lower bounds of S is then non-empty. So sort of pictorially, based on our intuitive picture, if the set S comprises these orange points, then a lower bound is anything to the left of this set because it's less than or equal to each of the members of this set. So for example, this green point L serves as a lower bound of S. Similarly, L prime, this green point is also lower bound. And in fact, any point on this ray which is on the left of this set will serve as a lower bound. So that's the mental picture that we have. But let's see some concrete examples. So suppose we take S to be the finite set comprising the 3 points 1, 2 and 9. Then any L, any real number L which is less than or equal to 1 is a lower bound, because any such real number being less than or equal to 1 will certainly be less than or equal to each of the members of this set, and so it will serve as a lower bound. Let's take one more example. Let S be the set of those real numbers x such that x is strictly bigger than 0. In other words, x is positive. Now any real number L which is less than or equal to 0 will be a lower bound for this set S, because if you have any element of the set, then it will be positive, so it will be bigger than this 0 and hence also bigger than or equal to this L. So in other words, L will be less than or equal to every element of the set, and so any such real number is going to be a lower bound of S. If I look at the set of all real numbers, then we claim that it's not bounded below, and the proof is very similar to what we did for showing that the set of real numbers is not bounded above. So let L be a lower bound of this set of real numbers, but then L minus 1 is also a real number, right? And since L was supposed to be a lower bound of this set, this L will be less than or equal to each real number, in particular less than or equal to L minus 1, because L minus 1 is a real number. So we get the inequality that L is less than or equal to L minus 1, okay, and if I subtract L on both sides, I get that 0 is less than or equal to minus 1, which is absurd. Okay, so this contradiction shows that this L cannot be a lower bound, and so this set of real numbers has no lower bound. And for the empty set, one can show that every real number is a lower bound, and the proof is very similar to what we did to show that for the empty set, every real number serves as an upper bound. So by now we know what's meant by the upper bound of a subset of R, what's meant by a subset of R being bounded above, we know what's meant by the lower bound of a subset of R, and what's meant by a subset of R being bounded below. So now here is one more definition. If S is a subset of R, then we say that it is bounded if it is both bounded above as well as bounded below. Okay? So if you look at these examples, one can see that since this set is bounded above as well as bounded below, this is a bounded set. If I look at this set, we have just shown that it is bounded below, but you can show that this set is not bounded above, and so this set is not bounded. Similarly, the set of real numbers is also not bounded because it is neither bounded below nor bounded above. On the other hand, the empty set is bounded because it is bounded above as well as bounded below. So our goal is to understand what's meant by the least upper bound property of R, and by now we know that if you have a subset S of R, what is meant by an upper bound for this subset of R. Now let us understand what's meant by the least upper bound of a subset of R. So it's what the name indicates, and here is the precise definition. So suppose that S is a subset of R, then a real number U star is said to be a least upper bound of S, or sometimes it's also called the supremum of S, if two things happen. First of all, this U star is an upper bound of S, and moreover it's the least one in the sense that if U is another upper bound of S, then this U is bigger than U star. Okay, so U star is less than or equal to U. In other words, it's the least one. Okay. Alright, so here is the mental picture that we have, intuitive picture. So here is the real line, and suppose that these orange points are the points in S. Then we know that upper bounds are points to the right of S. They are bigger than each element of the set. So here are some upper bounds. This U serves as an upper bound, this U prime serves as an upper bound, and in fact all the points on the right of this S, they serve as upper bounds. Now the least among these, sort of the leftmost one, is this U star. That's the least upper bound. Okay. This is the intuitive picture that we have, and let's see some examples. So let us consider again the set, which is the finite set consisting of 3 points, 1, 2 and 9. Then we claim that U star is equal to 9 is a least upper bound of S. Okay, so to prove this claim, we have to check two things. For something to be the least upper bound, two things have to happen. First of all, it should be an upper bound, and if you have any other upper bound, then that number should be bigger than this least upper bound. Okay, so first of all, U star equal to 9 is an upper bound. Indeed, it's bigger than each of the members of the set. Now we have to show the second thing, namely that if U is any other upper bound of S, then we want to prove this inequality, that this U star, which is 9, is less than or equal to U. But we know that 9 belongs to the set, and we know that this U is an upper bound, so this U should be bigger than each member of the set. In particular, it should be bigger than or equal to this 9. And so you know that this U is bigger than or equal to 9 which was our candidate for the least upper bound. And so we have proved two things. First of all, this u star equal to 9 is an upper bound, and moreover, if you have any other upper bound u, then that u is bigger than or equal to this u star, which is 9. So this u star is a least upper bound of S. So let's see one more example. So this is a set that we had considered earlier. The set S is the set of all real numbers x which are strictly less than 1. So all the points on this array which are less than 1 belong to this set. So the point 1 is not included. And then we had seen that all the real numbers which are bigger than or equal to 1, they serve as upper bounds for this set. So all the points on this green ray, including the point 1. Clearly the smallest among these upper bounds is u star equal to 1, and so we suspect that u star equal to 1 is a least upper bound of S, and now let us prove this claim rigorously. So to show that u star is a least upper bound of S, we have to prove two things. One, that it's an upper bound of S, and secondly, if u is any other upper bound of S, then this u is bigger than or equal to 1. Now the fact that u star is equal to 1 is an upper bound of S we had seen earlier. Now let us show that if u is an upper bound of S, then this u is bigger than or equal to 1. Now to show that u is bigger than or equal to 1, we will prove this by contradiction. So let us suppose that it is not the case that u is bigger than or equal to 1. But then by the trichotomy law, the only option is that u is strictly less than 1. So here is 1. And now if u is strictly less than 1, then we see that it enters the set S, and so there are points which are in between this u and 1, which will be in S, but u was supposed to be an upper bound, so that was supposed to be bigger than all the points of S, but here we see that it is less than these points. So that's going to be the source of our contradiction. So in fact, if we take any point in between u and 1, that will lead to a contradiction. So why not take u plus 1 divided by 2? So something midway between this u and 1. So first of all, let us show that this u plus 1 divided by 2 is an element of S. Now to show that something is an element of S, we should show that it is strictly less than 1. So the question is u plus 1 by 2 strictly less than 1? And the answer is yes, because we are assuming that u is strictly less than 1. So this u is strictly less than 1. So if I replace that, then u plus 1 by 2 is strictly less than 1 plus 1 by 2, and 1 plus 1 by 2 is equal to 1. So indeed this is strictly less than 1, and so it belongs to S. But now this u was supposed to be an upper bound, so it should be bigger than or equal to all the members of the set, but we visibly see that this u is in fact strictly less than this member of S, and that's going to be our contradiction. So let's note that this u is u plus u by 2. And since u is assumed to be strictly less than 1, this is strictly less than u plus 1 by 2. And this is our element in S. We have just seen that. So this u cannot be an upper bound because it is not bigger than or equal to this member, but the exact opposite. It is strictly less than this. So we get that u is not an upper bound of S, which contradicts this fact that u is an upper bound of S. So if we assume this, then we arrive at a contradiction. So this can't be true. And so u has to be bigger than or equal to 1. So we have shown that this u star equal to 1 is an upper bound of S, and whenever u is any other upper bound of S, then this u is bigger than or equal to this 1. And so 1 is a least upper bound of S. Now this kind of arguments we will have to give in this course often, and the first time you see this might seem more complicated than it really is, but as the weeks go by, we will get more and more practice with examples and exercises and so on, and we'll get better at it. And this kind of an argument will then seem quite natural with practice. Let's consider one more example. Suppose I take the set S to be the set of all real numbers. Then we had seen earlier that this set does not have an upper bound, and so it can't have a least upper bound either, because a least upper bound should first of all be an upper bound, but since this set has no upper bounds, it cannot have a least upper bound. So as our final example, let us consider the empty set. Now earlier we had seen that every real number u serves as an upper bound for this set. So if we think of all the upper bounds on the number line, then we get the whole number line. And the least upper bound is supposed to be the smallest among these, but of course this set has no least element. So we suspect that this empty set does not have a least upper bound. Okay, so now let us prove that rigorously, and we'll prove this by contradiction. So suppose on the contrary that u star is a real number which is a least upper bound of this empty set. Then u star being a real number, u star minus 1 is also a real number, but every real number is an upper bound, so this u star minus 1 is an upper bound for this empty set. But u star is supposed to be the least upper bound, so this u star is going to be less than or equal to any upper bound, in particular this upper bound. So this u star is going to be less than or equal to u star minus 1. Okay, so we have got this inequality. And now if we add minus u star to both sides and add 1 to both sides, then this delivers that 1 is less than or equal to 0, but we know that 1 is strictly bigger than 0, so this is a contradiction. So we have arrived at a contradiction by assuming that there exists a least upper bound, and so this assumption cannot be true. So this set has no least upper bound. So although there are lots of upper bounds, there is no least upper bound for this set. Now we'll give a new definition. Just like among all the upper bounds of a set, one can talk about the least upper bound. In the same way, if a set is bounded below and there are lots of lower bounds, you can talk about the greatest one amongst these, and that's the notion of the greatest lower bound of a set. So here is the definition. So let S be a subset of R, then a real number L star is a greatest lower bound of S, or sometimes it's also called the infimum of S. If first of all L star is a lower bound of S, and moreover if L is any other lower bound of S, then this L star is bigger than or equal to this L. So this L star is the greatest among the lower bounds. And the intuitive picture that we have in mind is like this. So you have some set S which is bounded below, and there are lots of lower bounds, and then the greatest one amongst them, sort of the rightmost one, is the greatest lower bound of this set. So that's this L star. Okay, so we'll now prove a theorem which is related to the following question. Suppose you have a subset S of R which has a least upper bound, so it possesses a supremum. Then is this least upper bound unique? Can it have two supremums? And intuitively we expect the answer to be no, because if a set has a supremum, well, that's the least upper bound, so that's the smallest among all the upper bounds possessed by the set. You cannot have sort of two least elements for this set of upper bounds. So intuitively we expect this to be true, but let us now give a rigorous proof. So this theorem says the following: if S is a subset of R which has a supremum, then this supremum is unique. So let's give a proof of this. So suppose that u star and u star prime are two real numbers which are both least upper bounds of S. Okay, so in particular they are both upper bounds as well, and so u star prime is an upper bound of S, but u star is a least upper bound of S, and any least upper bound is less than or equal to any other upper bound, and since u star prime is an upper bound, we get that u star is less than or equal to u star prime. So what I'm using is the fact that this is the least upper bound and this is an upper bound of the set. Now this means that u star is either strictly less than u star prime or equal to u star prime, and so it is certainly not the case that u star is strictly bigger than u star prime by the trichotomy law. Okay, and similarly by swapping the roles of u star and u star prime, we also get this inequality. Okay, so the logic is that this u star, since it's the least upper bound of S, it is certainly an upper bound, so this is an upper bound, and u star prime is a least upper bound, and any least upper bound is less than or equal to any upper bound. So since this is an upper bound and this is a least upper bound, u star prime is less than or equal to u star. And since we know that u star prime is less than or equal to u star, then we know for sure that it is not the case that u star prime is strictly bigger than u star by the trichotomy law. So what we have got for these two numbers u star and u star prime is that we know that it is not the case that u star is strictly bigger than u star prime, and it is not the case that u star prime is strictly bigger than u star. So by the trichotomy law again, the only choice that we have is that u star is equal to u star prime. Okay, or if you like, from these two put together, we can conclude that u star is equal to u star prime. So these two least upper bounds are the same, and so we have shown this uniqueness. So if a subset of R possesses a least upper bound, then it is unique, and this unique number is denoted by this supremum of S, this notation. So the supremum of S is the real number which is the least upper bound of S, of course, if it exists. And just like we proved that any set which has a supremum has a unique supremum, in the same way any set which has an infimum or a greatest lower bound has a unique greatest lower bound. A similar proof can be given in that case. And this unique number is then denoted by inf S. Okay, so inf S means the greatest lower bound of S, of course, provided it exists. So let us visit our earlier examples. So let's consider this finite set comprising just the three elements 1, 2 and 9. Then we had seen that this set has a supremum, it is equal to 9, and so we write sup of this set is equal to 9. And let's note that this 9 actually belongs to the set. So we have that the supremum of this set is in fact an element of the set S itself. Okay. As another example, let's revisit this one, namely the set of all real numbers x which are strictly less than 1. Then we had seen that this has a least upper bound which is equal to 1, and so we write sup of this set is equal to 1. And let's now note that this supremum is not an element of the set because 1 is not strictly less than 1. So this supremum does not belong to the set. So these two examples show that in some instances the supremum of a set belongs to the set and sometimes it does not belong to the set. And in some situations it's convenient to keep track of when the supremum of the set belongs to the set. For example, in the subject of optimization, and so we introduce the notion of the maximum of a set. So here is the definition. So suppose that S is a subset of R, and let us suppose that the least upper bound of this set exists. So the supremum of this set exists. And let us also suppose that this supremum of S, which is a real number, is in fact an element of the set S itself. So then we say that the supremum of S is the maximum of S. And sometimes we use the notation max S. Okay, so that's just the supremum of S, this real number, provided that the supremum of S is an element of the set S itself. And similarly, we can also give the definition of the minimum of S. So if the infimum of the set exists and in fact it is an element of the set itself, then we call the infimum of S the minimum of S, and sometimes we use the notation min S. Okay, so that's just the infimum of S when the infimum of S is an element of the set itself. Okay, so at long last, we are now ready to understand what is the statement of the least upper bound property of R. So this is the property of R which makes calculus work, and this property is not possessed by some simpler number systems. For example, the set of rational numbers, which is simpler than R, that does not have a corresponding property, but the set of real numbers have this property. So what does this property say? It says that every non-empty subset of R which is bounded above has a least upper bound. Okay, so if you have a subset S of R which is not empty and which is bounded above, so it has an upper bound, then in fact it has a least upper bound. Okay, so let's see some examples. Let's revisit our examples and see what happens there. So if I look at the set S, which comprises just the three numbers 1, 2 and 9, then clearly this set is not empty, just like demanded over here. It is bounded above, and we had seen earlier that this does have a least upper bound. In fact, it is equal to 9. So it's no surprise that over here it works, because this statement in fact guarantees that it had to have a least upper bound, and earlier we had seen that in fact 9 is a least upper bound. Let's look at this example now. This is also a set we had considered before. The set S is given by the set of all real numbers x which are strictly less than 1. Now this set is non-empty. For example, 0 belongs to it. 0 is strictly less than 1. It is bounded above. Any number u which is bigger than or equal to 1 serves as an upper bound of this set. Okay, so this is also true. And so it should have a least upper bound by this statement. And indeed we had seen earlier that the supremum of this set does exist and it is equal to 1. So now let's look at the set S, which is the set of real numbers. Now, this set is again non-empty. For example, 0 belongs to it. But this set is not bounded above. This we had seen earlier. And we had also seen that this set has no least upper bound, because any least upper bound should first of all be an upper bound, but this set has no upper bound at all. So the supremum of S does not exist. But there is no contradiction with this statement, because all that this says is that when you have a non-empty subset of R which is bounded above, then a least upper bound is guaranteed, but this set was not bounded above. Okay, so there is no contradiction with this statement. And as our final example, let's consider the empty set. Earlier we had seen that this has no least upper bound, and again there is no contradiction over here, because this says that only when you have a non-empty subset of R which is bounded above, then a least upper bound has to exist. So although for this set we know that it is bounded above, any real number serves as an upper bound, so this part is okay, but the set is empty, so this part is violated. And what this statement is saying is that only when you have a non-empty subset of R which is bounded above, there exists a least upper bound, but this set is empty. Okay, so it's no surprise that the supremum of S does not exist in this case. Alright, so this is the least upper bound property of R, and as we proceed in this part on analysis, we will see that this property we will use again and again in crucial theorems, and this is the thing which makes calculus work and allows us to prove these nice theorems in calculus. So this property is not possessed by some other number systems. For example, the simpler set of rational numbers, that does not possess the least upper bound property. So we will now see an example of this, and in the motivational remarks, when we looked at that problem where we were computing the area under the graph of the function 1 by x between 1 and 2, there we had encountered this set of rational numbers a1, a2, a3 and so on, which was bounded above. Okay, so it was a set of rational numbers, it was a subset of the set of rational numbers which was bounded above, but it can be shown over there that there is no rational number which is the least upper bound of that set. Okay, however, in the set of real numbers, there does exist a least upper bound for that set. Okay, but now let me give you a concrete example of a subset of the rational numbers such that it does not possess a rational least upper bound. Okay, and this we will actually prove. Okay, so we'll now consider an example which shows that Q does not have the least upper bound property. So in this example, we will consider a set S, which is a subset of the set of rational numbers. It is non-empty, it is bounded above, but the least upper bound of this set does not exist in the set of rational numbers. Okay, so we will show that this set has no rational least upper bound. Okay, and that will show that Q does not have the least upper bound property. So as the set S, we consider the set of all those rational numbers whose square is less than or equal to 2. So this set is the set of all R in Q such that R square is less than or equal to 2. Let us first note that this set is not empty, because 1 belongs to S. Indeed, 1 is a rational number, and if I square this, 1 square is just equal to 1, and that is indeed strictly less than 2, so it's less than or equal to 2. So this 1 belongs to S. Let us now show that the set S is also bounded above, and we'll show in fact that this number 2 serves as an upper bound. So what we want to show is that for every R belonging to S, you have that R is less than or equal to 2. So let us suppose that this is not true. So that means that there exists an element R in S such that this does not hold. In other words, R is strictly bigger than 2. But then if I square R, I get that R square is bigger than 2 square, but 2 square is equal to 4, which is strictly bigger than 2. And so you get that R square is strictly bigger than 2. But then R cannot belong to S, because anything in S has its square which is less than or equal to 2, whereas here you have the square of R is strictly bigger than 2. And so R does not belong to S. But that's a contradiction to the fact that R belongs to S. So if we assume that R is bigger than 2, then we arrive at a contradiction, and so this cannot happen. So R has to be less than or equal to 2. And so we have shown that S is indeed bounded above because it has this upper bound which is 2. So this set is non-empty and it is bounded above, but now we will show that it does not possess a rational least upper bound. Now we will show this by contradiction. So let us suppose that u star is a rational number which is the least upper bound of S. Okay, and we will arrive at a contradiction. So we'll first prove the claim that u star square is equal to 2. And we'll show this by showing that u star square strictly less than 2 and u star square strictly bigger than 2 are both impossible. And then by the trichotomy law, it will follow that u star square has got to be equal to 2. And let us also note a fact that we will soon use, that since u star is assumed to be the least upper bound of S, in particular it's an upper bound, so that u star is going to be bigger than or equal to each element of S. But we have noticed that 1 belongs to S, so we know that this u star is going to be bigger than or equal to 1, because this is the least upper bound, so in particular it's an upper bound and this is an element of the set. Okay, so we have defined this non-empty subset S of rational numbers, and we have seen that it is a non-empty subset and it is bounded above, and we are assuming that it possesses a rational least upper bound u star, and we are in the process of proving that then this u star satisfies u star square is equal to 2. And the way we are going to do this is by showing that both of these cases, u star square is strictly less than 2 is impossible, and also u star square strictly bigger than 2 is also impossible, and that will mean that u star square has got to be equal to 2. Okay, so that's the plan. So to do this, we will consider this rational number which is given by 2 times u star plus 1 divided by u star plus 2. So let us first notice that we had just seen that u star is bigger than or equal to 1, in particular positive, so this denominator is nice and positive, and so is the numerator. So this overall expression r is a positive number. Moreover, since u star is a rational number, this r is also a rational number. So it's a bit of a mystery why we are considering this r, but let us accept that for now and see if we understand the rest of the proof, because the point is really to show that Q does not have this least upper bound property via the consideration of this set. Okay, so indeed this construction is a bit out of the blue, but we accept that for now. So we have just seen that this r is a positive rational number, and let us also calculate r square minus 2 because it will be needed in what is to follow. So if we substitute the expression for r from over here and do some algebra, so it's a good idea to pause the video and do it yourself, then you will end up with this expression 2 times u star square minus 2 divided by u star plus 2 the whole square. Okay, so this expression will be needed in what is to follow. So let us first consider the case that u star square is strictly less than 2, and we'll show that this case is impossible by showing that assuming this leads to a contradiction. Okay. Now if u star square is strictly less than 2, that means that this numerator is strictly less than 0. Meanwhile the denominator is positive, so this overall expression is strictly less than 0. That means that r square minus 2 is strictly less than 0. In other words, r square is strictly less than 2. But r was a rational number, and now we have discovered that its square is strictly less than 2. So that means that r belongs to S. After all, S was the collection of all those rational numbers whose square is less than or equal to 2, and here we have got a rational number whose square is strictly less than 2, hence less than or equal to 2, and so this r is in S. But we had assumed that u star is the least upper bound of the set, so in particular it's an upper bound, and so this u star is bigger than all of the members of S. In particular, it will be bigger than or equal to this member of S. So we have the inequality that r is less than or equal to u star. But if we substitute the expression for r, then this inequality becomes this one, and if I multiply both sides by this positive number 2 plus u star, then the inequality will be preserved. But we then note that on the one side you will get 2 u star, and on the other side also you will get 2 times this u star. So those will cancel, leaving 2 is strictly less than or equal to u star square, okay, namely this one. So you can check that for yourself. And so you have got that 2 is less than or equal to u star square. But we had that u star square is strictly less than 2, and now we are getting the exact opposite. So this is obviously a contradiction, and so this case cannot happen, because if we assume that, then we get a contradiction. So this case is not possible, and now let us also show that u star square strictly bigger than 2 is also not possible. So if u star square is strictly bigger than 2, that's the same as saying that u star square minus 2 is strictly bigger than 0. So this numerator is positive and so is the denominator, and so this overall expression is positive now. So you have that r square minus 2 is strictly bigger than 0. In other words, r square is strictly bigger than 2. Now we claim that r is an upper bound of S. What does it mean to say that r is an upper bound of S? That means that no matter which element r prime you take in S, this r prime is less than or equal to this claimed upper bound, which is r. So let's prove this. So we want to show that whenever r prime is in S, r prime is less than or equal to r. So this is what we want to prove, this box statement. Now what's the contrapositive of this? It's that whenever this does not hold, this cannot hold. In other words, whenever r prime is strictly bigger than r prime does not belong to S. Okay, so this box statement is the contrapositive of this. So let's just prove this, because that's the same as proving this. So let's suppose that r prime is strictly bigger than r, and r we knew was positive. Okay, so we have that this is true. Now if I multiply both sides of this by r prime, I get r prime square is bigger than r prime times r. And if I multiply both sides of this by r, I get r prime r is bigger than r square. Okay, so we have got this. And we also knew that r square was strictly bigger than 2. So we have got that r prime square is strictly bigger than 2. And so r prime cannot belong to S, because for something to belong to S, its square must be less than or equal to 2, but here you have that r prime square is actually strictly bigger than 2. Okay, so r prime does not belong to S. So we have shown this, which is the same as saying this, which was the same as saying that r is an upper bound of S. So we have got that this r is an upper bound of S, but this u star was the least upper bound of S, and so this u star must be less than or equal to any upper bound, in particular this upper bound r. So you have got that u star is less than or equal to r. But if we substitute what this r was, that was this expression, so you have got this. And again, by multiplying both sides by this positive quantity u star plus 2, we will get that u star square is less than or equal to 2. On the other hand, we had that u star square is strictly bigger than 2, and so we have now got the exact opposite of that. So that contradicts this, and so this cannot be true. So we have got that this is not true and this is not true, and so by the trichotomy law, the only choice which is left is that u star square is equal to 2. So we have got that we have this rational number u star, which is the least upper bound, its square is equal to 2. But we know that there is no rational number whose square is equal to 2, and so we have arrived at a contradiction. So this contradiction shows that our original assumption that there exists a rational number which is the least upper bound of S cannot be true, and so this subset S of Q does not have a rational least upper bound. Okay, and hence Q does not have the least upper bound property. And of course, this particular set is of course also a subset of R. It is still non-empty, it's still bounded above by 2. And so by the least upper bound property of R, the supremum of S exists as a real number. So the supremum of this set then exists by the least upper bound property of R. And if you call that supremum as u star, then you can still show that that u star satisfies u star square is equal to 2. And in fact, that supremum is then the square root of 2. Okay. So the supremum of this set does exist in the set of real numbers, but it does not exist in the set of rational numbers. So that concludes today's lecture, and what we have learned today is essentially we have understood what's the least upper bound property of the set of real numbers, and next time we will look at further consequences of this.